The topic is plane waves in good conductor. As we know that in a good conductor, the loss tangent is very high. So that in this case, sigma is greater than omega epsilon. This means the medium, that is good conductor, depend upon the low frequencies. So here we talk about the plane waves in good conductors first, and then we talk about a skin effect. This effect is introduced only in good conductors. So we first see some characteristic of a good conductor in terms of alpha, beta and intrinsic impedance, and then we talk about a skin effect. So here in case of good conductors, the ratio, that is sigma upon omega epsilon, is greater than 1, means the loss tangent tan theta is very large. And we know that in a good conductors the conductivity is very high, that approaches to infinity. This is the first condition of a good conductor, that is the conductivity is very high, approaches infinity. And the second condition is here the permittivity epsilon is equals to epsilon naught. Here the relative permittivity of a good conductor is 1. Also the permeability mu equals to mu naught into mu r. So this is a condition for a plane wave propagate in a good conductors. In this case the loss tangent is very large, so that sigma value is greater than omega epsilon, and this introduces a low frequency. Now as we know that the propagation constant is denoted by gamma, and it is equals to under root of j omega mu within bracket sigma plus j omega epsilon. This propagation constant is introduced in a practical case, that is for lossy dielectric. So here we take this formula, and after putting the conditions of the good conductor we can get a propagation constant. So here we see that the formula of gamma is, that is propagation constant, is under root of j omega mu within bracket sigma plus j omega epsilon. Now we apply a condition of a good conductor, that is ratio sigma upon omega epsilon greater than 1. For this we take sigma as a common within a square bracket, so we get under root of j omega mu sigma within bracket 1 plus j omega epsilon upon sigma. So here we know that for a good conductor the ratio sigma upon omega epsilon is greater than 1, or we can say that the ratio omega epsilon upon sigma is less than 1. So from here, as for a good conductor the ratio omega epsilon upon sigma is less than 1, so it approaches 0. So we get only the value of gamma, that is approximate value of gamma, is equals to under root of j omega mu sigma. This is because the ratio omega epsilon upon sigma is very small than 1, and means 1 is greater than this value. So this omega epsilon upon sigma is very small, so we neglect it and we get only under root of j omega mu sigma. And we know that the propagation constant gamma is a complex quantity, it has a magnitude and phase. So the magnitude of this propagation constant is under root of omega mu sigma, and the phase of this gamma, that is theta suffix gamma, is 45 degree. So how we get this? Let us see. So we know that in case of propagation constant gamma, which is equals to alpha plus j beta, alpha is called the attenuation constant and beta is called a phase constant. And we know that the formula of alpha is equals to omega under root mu epsilon upon 2 within bracket under root 1 plus sigma upon omega epsilon whole square minus 1. So here the ratio, that is sigma upon omega epsilon, is greater than 1. So this value is very large as compared to 1. So 1 is neglected here, and we get within under root, that is sigma upon omega epsilon whole square. That is sigma upon omega epsilon, and we get alpha equals to omega under root mu epsilon upon 2 within bracket sigma upon omega epsilon. This is because the ratio sigma upon omega epsilon is greater than 1. So after putting this relation of a good conductor in the formula of alpha, we get this. And outside this square bracket there is omega. So we take it inside the square root. It becomes omega square. So 1 omega is cancelled here and we get alpha is equals to under root omega mu sigma upon 2. We can write omega equals to 2 pi f. So 2 is also cancelled and we get under root of pi f mu sigma. This value is same as that of beta here because we know that the formula of beta is omega under root mu epsilon upon 2 within bracket under root 1 plus sigma upon omega epsilon whole square plus 1. Only the difference is minus in case of alpha and plus in case of beta, and for good conductor the ratio sigma upon omega epsilon is very large as compared to 1. So 1 is cancelled here and we get the same formula as that of alpha. So beta is also equals to under root of omega mu sigma upon 2. When we put omega equals to 2 pi f, we get under root pi f mu sigma. So we get alpha equals to beta equals to under root pi f mu sigma. Now as we know that gamma is equals to alpha plus j beta, and gamma is a complex value, complex variable. It has a magnitude and phase. So to determine the magnitude of gamma, we take a mod of gamma, and this is equals to under root of alpha square plus beta square. After putting the value of alpha and beta in case of mod of gamma, we get under root of omega mu sigma. And to get the phase, that is theta suffix gamma, we take tan inverse of beta upon alpha. So after putting the value of beta alpha, that is same, we get tan inverse 1, and this value of phase, that is theta suffix gamma, is 45 degree. So in this way we get a phase that is 45 degree. Next formula is wave velocity. Wave velocity is denoted by small u, and it is a ratio of omega upon beta, and the value of beta in case of good conductor is under root of omega mu sigma upon 2. So after putting the value of beta, we get a wave velocity that is under root of 2 omega upon mu sigma. The next is the wavelength lambda, that can be determined by taking a ratio 2 pi upon beta. And the next is the intrinsic impedance of a good conductor. As we know that the intrinsic impedance is denoted by eta, and it is equals to under root of j omega mu upon sigma plus j omega epsilon. And this intrinsic impedance is a complex quantity, so it has a magnitude and phase. So the magnitude of intrinsic impedance is denoted by mod eta, and the phase is denoted by theta suffix eta. So for a good conductor, as we know that the ratio sigma upon omega epsilon is greater than 1, so we apply this condition, that is for good conductor. For this, in a intrinsic impedance formula, we divide numerator and denominator by j omega. So we get under root of mu upon sigma upon j omega plus epsilon. We again take epsilon as a common in the denominator, and we get under root of mu upon epsilon within bracket 1 upon 1 plus sigma upon j omega epsilon. Now we can use this condition of good conductor, that is sigma upon omega epsilon is greater than 1. Means this ratio is very large as compared to 1, so 1 is cancelled here and we get under root j omega mu epsilon upon sigma epsilon. So here epsilon is cancelled here and we get the intrinsic impedance for a good conductor, that is under root of j omega mu upon sigma. Here we use a condition of a good conductor, that is sigma upon omega epsilon greater than 1. Now the intrinsic impedance is a complex variable, it has a magnitude and phase. Now we find magnitude of intrinsic impedance denoted by mod of eta, and it is equals to, numerator is under root of mu upon epsilon and denominator is 1 plus sigma upon omega epsilon square and whole to power 1 by 4. Because in case of intrinsic impedance there is a under root, and to determine the magnitude there is again under root, so the denominator power is 1 by 4. Okay. Now to determine the intrinsic impedance magnitude, that is mod of eta, we apply a condition of a good conductor, that is the ratio sigma upon omega epsilon is greater than 1. So here in case of mod eta, the sigma upon omega epsilon is greater than 1. So we neglect 1 as compared to this ratio, and we get only in the denominator we get sigma upon omega epsilon square whole to power 1 by 4, and it becomes, the denominator becomes sigma upon omega epsilon to power 1 by 2. So 1 by 2 is the under root, so the mod of eta is equals to under root of mu omega upon sigma only. Here epsilon is cancelled. So in this way we get a magnitude of intrinsic impedance in case of conductor, and for a conductor the condition is sigma upon omega epsilon is greater than 1, and we know that the phase of this intrinsic impedance for a good conductor is 45 degree. As the range of theta suffix eta is greater or equals to 0 and less than or equals to 45 degree. This value 45 degree is for good conductor and 0 degree is for good dielectric. So here we note one point. For a good conductor the phase of intrinsic impedance is 45 degree, and for a good dielectric the phase of the intrinsic impedance is 0 degree. So here we observe that the electric field leads magnetic field by 45 degree. This is because we know that the intrinsic impedance is the ratio of E naught upon H naught. So we can say that the electric field leads magnetic field by 45 degree in case of good conductor. So the equation of electric field E vector equals to E naught e to power minus alpha z cos omega t minus beta z unit vector x, and the value of H vector is equals to E naught upon under root omega mu upon sigma e to power minus alpha z cos omega t minus beta z minus 45 degree unit vector y. Since we know that eta is equals to ratio of E naught upon H naught, so in place of H naught we can write E naught upon eta, and eta is a complex variable, it has a magnitude and phase, so in place of magnitude, that is mod eta, we can write under root of omega mu upon sigma, and we take a phase to the numerator side, so its signs get changed and we get a phase, that is cos within bracket omega t minus beta z minus 45 degree. Here the electric field is polarized to unit vector x and the magnetic field is polarized towards unit vector y, and the electric field leads magnetic field by 45 degree. So from these two equations, that is a time varying electric field and magnetic field, we observe that the amplitude is attenuated by a factor of e to power minus alpha z. Here the alpha is called the attenuation constant. So the amplitude of electric field is E naught, that is attenuated by a factor of e to power minus alpha z, and also the amplitude of the H vector attenuate by the factor of e to power minus alpha z. This is a relationship of electric field in magnetic field in case of good conductors. Now we introduce a effect that is called a skin effect or skin depth. As we take the equation of electric field, that is E vector, and in this the amplitude is attenuated by a factor of e to power minus alpha z. So from here the amplitude at z equals to 0, that is when this is at the origin, we have amplitude E naught, and as the wave propagates towards the z direction, this amplitude attenuate decreases as wave propagates along z direction. So here at some distance, that is at a distance of del, the wave amplitude decreased by a factor of e to power minus 1. E to power minus 1 means about 37% of the original value, and this is called a skin depth or penetration depth of the medium. Means to determine the skin depth or penetration depth of the medium, we take a factor that is e to power minus 1. To get e to power minus 1, we put z equals to del, and to determine e to power minus 1, we put del is equals to 1 upon alpha, so that the value of alpha get cancelled and we get e to power minus 1, and e to power minus 1, the value is 37% of the original value. So the definition of the skin depth is, the skin depth is the distance along z direction and it is denoted by del, and through this distance the wave amplitude decreases by the factor of e to power minus 1, that is about 37% of the original value, and this is called a skin depth or penetration depth of the medium. So here the distance del is equals to 1 upon alpha, and this penetration depth or skin depth measures the depth to which the electromagnetic wave can penetrate the medium. Means the electromagnetic wave can penetrate inside the medium, inside the conductor, and how much it penetrates the conductor, that can be measured by a term that is called a skin depth or penetration depth, and it is generally a ratio that is inversely proportional to alpha, and this condition is valid for any material medium. So for a good conductor, as we know that the value of alpha is under root of omega mu sigma upon 2, so the penetration depth del is equals to under root of 2 upon omega mu sigma. So the conclusion is that when the propagation is in good conductor, the loss tangent, that is tan theta, is very large. That is, the ratio sigma upon omega epsilon is greater than 1, and this introduces a low frequency. And also we know that the loss tangent tan theta is the ratio of epsilon double dash upon epsilon dash, that is equals to sigma upon omega epsilon. Here the value of epsilon dash is epsilon and epsilon double dash is sigma upon omega. So from here the ratio sigma upon omega epsilon is greater than 1, and this is a more specific criteria of a good conductor. Now we note one point. As we know that the uniform plane waves are associated with electromagnetic fields, that is the time varying electric field and time varying magnetic field. These time varying fields existing in the external dielectric that adjoins the conductor's surface. As we know that the electromagnetic wave propagates through a transmission line, and in a transmission line there is a two concentric cylinder that are of a good conductor, and here the conductivity of a good conductor is very high as compared to omega epsilon, and in between these two concentric cylinders there is a dielectric. Here the dielectric adjoins the conductor surfaces, and as the electromagnetic wave propagates along the conducting surfaces, it suffers a losses that is called a dissipated losses, that is due to the conduction current. Conduction current generates on the surface of the conductor during the propagation of wave. Due to that conduction current there is a loss, and that loss is due to the resistance parameter of the transmission line. Due to this loss, the electromagnetic field attenuates as it propagates along a distance of the transmission line, and this effect is called a skin effect of a good conductor. So here the good conductor has high conductivity as well as a large conduction current. So here we note point, the energy represented by the wave traveling through the material decreases as the wave propagates because ohmic losses are continuously present. For example, here we take a good conductor, that is a copper one, and when we take a copper as a conducting material in a transmission line, all the electromagnetic fields are tends to 0 at a distance greater than few skin depth from the surface. Means inside the conductor up to a certain distance that is greater than a few skin depth, all the electromagnetic fields tends to 0. And we know that in electromagnetic field there is electric field intensity and magnetic field intensity. That magnetic field intensity is due to the current density. So any current density or electromagnetic field intensity at the surface of a good conductor decays rapidly as we progress into the conductor, means inside the conductor, depth of the conductor, and the electromagnetic energy is not transmitted in the interior of the conductor. It only travels in a region surrounding the conductor and the conductor only guides that way, and that is called a guided propagation. So this is about the wave propagation in good conductors and the effect in a good conductor, that is a skin effect or a skin depth or penetration depth.